In this video, we're going to talk about sunspots and what they are. Sunspots are regions on the sun in the photosphere where some areas are lower temperatures than the surrounding areas. And what happens there is that causes the region to appear dark on the sun. What astronomers think is happening is that the magnetic field is preventing the heat in the convection zone from rising up to the surface, and that prevention of heat causes a cooler region to appear on the surface of the sun. And that's why you see the dark areas within that. On the left, we have a picture of a single sunspot, and on the right, we have a picture of a group of sunspots. Each sunspot consists of an umbra and a penumbra, which is the outer section of that sunspot. The umbra is going to be the cooler region that's in the middle, and the penumbra will be the outer region that's a little bit hotter than the umbra, but it's still going to be cooler than the surrounding granules that are on the sun here. When astronomers track sunspots, they can actually watch them move across the sun. And the reason this happens is because the sun actually rotates just like our Earth. The sun's rotation is going to be different at different latitudes of the sun. Just like we think on Earth, our latitudes go up and below the equator, the sun also has latitude from its equator. And those different latitudes are going to be rotating at different speeds. And that's what actually carries those sunspots across the surface. If you look at the image here, we're tracking sunspots over the course of about 10 days. In the first photo, we don't really see anything. But just after a few days, our group of sunspots starts to appear off the left side. As the sun continues to rotate, it brings those sunspots around. You can even see that there is some change within the sunspots on each day. Some might appear that weren't there before, but generally you can see the whole pattern moving across as the sun rotates. Now, if we were to go and look at the sun, we're not always going to see sunspots. The sunspots depend on where we're at in what's called the solar cycle. Now, there's a maximum sunspot time and then a minimum sunspot time for those sunspots, and that occurs over the course of about 11 years. And so we can go from low to high to low all within an 11-year cycle. On the left, we have a picture that shows what sunspots would look like at solar maximum. You can see there's a lot of activity within that picture and a lot of dark regions on the surface of the sun. On the right, we have what's called sunspot minimum or solar minimum, where there's not a lot of activity. You can still have a few sunspots on there, but you're not going to have nearly the same amount as we would at maximum. Just last year, we were at solar minimum within our sunspot cycle. So we're still not going to see too many sunspots if we were to go look at the sun right now. I want to take a look at the 11-year cycle and show you kind of what that looks like here. On our graph, we can see as we go from about each decade or so that the number of sunspots will begin to increase and then dramatically decrease. And then it repeats that cycle. You can notice we have a pattern of decrease, increase, decrease, increase. And this isn't something that we figured out recently. Astronomers have known this for a long time. As long as they've been looking at sunspots, they've noticed that the patterns increase and decrease. You can see at the times where the number of sunspots is higher, that's what it would look like here on our picture of solar maximum. And then for solar minimum, that's what it's going to look like here when there's not as many sunspots. Something else that's interesting with sunspots is their location. If you look at our graph right here, the second one, this is called a butterfly diagram. It actually shows the location of the sunspots as they correlate to their maximum and minimum time periods. 90 degrees north refers to the top of the sun, and then 90 degrees south refers to the bottom, and then 0 degrees would be our equator, just like we have here on Earth. Now, if you notice, there's not really many sunspots near the top or the bottom of the sun. The sunspots actually exist within a region fairly close to the equator. If you notice, right here at 1880, when we look at our position of the sunspots, they start off both high and low compared to the equator. As we move through our solar cycle, then what ends up happening here is those sunspots start moving closer and closer to the equator until eventually about 10 years later, what will happen is that location flips. And so they start to appear up towards the top and the bottom again, around 30 degrees north and 30 degrees south. What's actually happening there is every 22 years, the magnetic field of the sun is flipping. So the polarities are changing. And because that's flipping, that's causing those sunspots to appear in different locations. So you may wonder how we know that the magnetic field plays a role with sunspots and how those two things are related. Well, if you look at the picture here on the left, you can see some of the sunspots that are located on here. We've got a few right here, and then another one right here, and then a small group up towards the top. This is a visible light spectrum image of the sun, and it's showing the location of the sunspots as we would see them in the visible spectrum. Now, there is a filter on this image to allow us to see those, but on the picture right here in diagram B, this is a magnetogram, which actually takes a picture of the magnetic field of the sun. And if you kind of line those up, you can actually see where those sunspots are. The magnetic field is showing a disturbance within that. So there's activity, magnetic activity, on the same spots as those sunspots. And that's how we kind of associate that the magnetic field is related to those, the activity of the sunspots. Now, remember when we said that the sun is rotating? Well, it's not rotating at exactly the same speed all the way around. Since the sun is a gas and it's fluid in its motion, those movements actually cause a disturbance in the magnetic field. If we look here on the first image, our magnetic pole runs from north through the south, just like on Earth. Well, since the sun is rotating, as it continues to rotate through, that's going to cause a disturbance in that magnetic line. And as it keeps rotating, we end up getting our magnetic line breaking apart. And so these the disturbances are created there, and it's not a consistent straight line. And so because of those differences there, that's going to cause that magnetic activity, and that's going to relate to where we see those sunspots occur. When sunspots do form, they often form in pairs. And the reason for that is because our magnetic line is coming up out of the sun, it has to go back into another location of the sun. So where it comes up and then over and then back into the sun, those two pairs are going to line up as the same pair of sunspots. If the magnetic activity is great enough of a disturbance, then we can actually get some of those sunspots to release a tremendous amount of energy. And we're going to talk about these next week, but we have what's called solar flares, prominences, and coronal mass ejections. And we've kind of talked about those briefly before during our APODs when we look at our pictures. But coronal mass ejections are a very serious release of energy that comes from the sunspots. And those are things that can significantly damage our satellites in space, and that can cause trouble with our communications. We are going to explore those more in depth, but we'll kind of talk about the anatomy of those. But I just want to look at a few more things that relate to the magnetic field with the sunspots. If we look at our image on the left here, this is another picture of a sunspot. The picture on the right is showing a magnetic spectrum and kind of showing you the iron absorption lines related to the magnetic field that's on top of that, or I guess below that sunspot. If we look at the regions that are dark within that sunspot, we can actually see that the magnetic absorption line goes from being a single line on the regions outside where there's not a lot of magnetic activity to a split here. And that's because of that rotation of the sun causing that magnetic line to break apart into multiple lines. So this really shows astronomers that there's a correlation between our magnetic field and the sunspots that are created on the surface of the sun. This is a diagram that shows us the rotation period for the different parts of the sun. You can see on the color scale here that towards the red is going to be about 25 days of rotation, and then all the way on the right, we've got about 35 days of rotation. So if we look at our diagram of the sun, it's going to be actually quicker closer to the equator that the sun is going to rotate, and the poles are going to be significantly slower. So the sun does rotate in different sections, we said. The fastest rotation is going to occur around the equator. So because of that sun's differential rotation, because it's rotating at different speeds, that's what's going to cause that magnetic line to break apart, and that's what's going to drive our sunspot activity. Now, why is any of this important? If we understand sunspots, then we can start to study the dangers that come with the release of that energy from those sunspots. When we start talking about solar flares, coronal mass ejections, these things that pose a danger to Earth. If we understand sunspots more in depth, then we can start to prepare our understanding of what causes those dangers to Earth, and then maybe we can study ways to find out how to protect ourselves from those. But we'll look more at these whenever we come back from Thanksgiving break.